All right, welcome back. Intro to Technology 1023. We're going to be talking about CPUs today. So, up to this point, let's back up a little bit. Most students coming into the Overstate program have been exposed to two things essentially: marketing and then general devices, and they tend to attach concepts to the device itself. So when they have something like headphones, like this, they don't necessarily understand how the headphones work. And why would they? They work. It's kind of like the microwave. As long as it warms the food, no one cares. Unfortunately, if you're going to be walking into this world, in this field, you're going to have to care about how the system works and how the parts actually work, right? So today we're going to be going over one of the primary components, which is the CPU. So CPU stands for Central Processing Unit, all right? What this thing does on a physical level is process electrical current. Voltage high equals 1, voltage low equals 0. Literally that simple. But if you do that a few billion times per second, which we're going to get into, you can create essentially anything, right? And this is software. This is exactly what software does. All right, so general specs, cores. And a lot of people get confused on this. So a CPU core is a physical node on a piece of silicon. Each core allows for an instruction to be processed. Okay, so if you have multiple programs running, which we all do at every single moment because it's Windows, it does a bunch of things in the background that you don't tell it to do, right? Or Mac does the same thing. Linux does too, just not as much. You're running lots of processes all at once. Okay, so you're going to need more than one core, which we'll get into. Multiple cores allows for instructions to be processed in parallel. So for a long time, especially in the early 2000s, if you're alive for that, your computer was single-threaded, had one core. So basically what that CPU had to do was every request that the OS or the software was requesting for had to be done one at a time. So whatever came through the stack gets processed in order. There is no, hey, split up this thing with do these things at the same time. There was no concept for that at the time. Well, there was, but not at the consumer level. Server level, a little bit different. Parallel processing has been around since the 70s. In consumer devices, that didn't happen until, especially all consumer devices, didn't happen until late 2000s. Okay. Hyperthreading. Hyperthreading is when you take a physical core and you separate it out into two logical cores. The concept behind this is that one core isn't always active. And what this allows you to do, and it comes at the cost of what is called switching, it allows you to run multiple things on a single core. It comes with a 10 to 30% performance boost depending on what you have and what architecture is on that particular CPU. Okay. Each hyper-threaded CPU is known as a thread, and the example down here at the bottom is if you had a 16-core CPU, which is a top-end consumer model at the moment, you would have 32 threads if it had hyper-threading, which the one I'm thinking of definitely does. All right. Clock speed measured in seconds, right? So how many cycles can you run per second? Now, we are far beyond the megahertz world at this point. I haven't seen a megahertz processor in probably 20 years. We are definitely in the gigahertz world. So 1 gigahertz is 1 billion cycles per second. That can't even fathom how fast that is. Most of our CPUs, especially mobile devices, are going to be 1.3 to 7 gigahertz on a low powered state. And then if we're talking about cell phone, you might get up to like 2.3, 2.5, something like that. If you're talking desktop or server, mostly desktop for high performance silicon, your base is going to start like 3.4, 3.5. If you get a top end model, it might be 3.9, 4.0. And then you can get a turbo of anywhere between 4 to 5, um, which is just insane. That's 5 billion cycles per second. Okay, so these are known as clock cycles, also known as ticks, depending on who you are talking to. Okay, a turbo, and this is relatively important because people get confused on this. A turbo is a automated overclock. What an overclock is, you take the base level speed, how many cycles per second, and then you just go faster. And this comes at a power difference. Uh, largely a power difference. So sometimes it's RAM limited. Sometimes it's thermally limited, but largely power and how much power the silicon can handle, and then how much heat you can dissipate. So, largely speaking, people get confused on this because it is, well, and it's largely due to marketing because your marketers are going to market the turbo speed and not the base clock. Um, so the turbo is abnormal. The turbo is typically one thread as well, and it doesn't apply to all the cores. So people get confused on that, and we'll cover it a little bit more, especially with our demonstration. If you're an Alpha student, and you're taking this physically. Okay, IPC, inputs per cycle. So this is another topic that people get confused on because you can run multiple things on a cycle. So how efficient are you per cycle, inputs per cycle? Uh, we are running up against a physical limit in terms of cycles that we can achieve per second. So a lot of the performance advantages that you're seeing year over year or biannually that are coming out from Intel and AMD typically comes from IPC and then architectural improvement or shrinking the node, which again, we're running up at a physical limitation there, and we'll go over that a little bit more here in a couple seconds because that's a different slide. Okay, IPC is measured on a average. Okay, performance of precise workloads needs to be tested. So CPUs, general compute units, the ones that we're used to, they're not very efficient, but they handle everything. So if you want to be extraordinarily efficient at one thing, you can make CPU and architectures ground up. ASICs is a good example of this for Bitcoin mining. You can be incredibly efficient if you have one task to do. Our CPUs can't do that. We ask it to do basically everything we throw at it, so it's not very efficient. So IPC is measured on a average, and that's a big part of it. How efficient can you be per cycle when you don't know what the software is going to request? Okay. General rule: higher the IPC, higher the clock, the better. Okay. Where these things start getting complicated is when you have a lower IPC but a higher clock, which this is what Intel is doing right now. They're just putting a bunch of power into their silicon. They don't have the IPC necessary to compete with AMD clock for clock. So they have a higher clock, lower IPC, and higher power draw, and they break about even with AMD at the moment. So yeah, it gets a little complicated, and we're definitely not going over how to measure these things. You just need to be aware of it. Again, as an intro to technology course, you just need to be exposed to some of these concepts. Okay. CPU specs, caching. So typically speaking, any consumer CPU is going to have 3 layers of cache: L1, L2, and L3. Obviously, L1 is the fastest, L2 next, and then L3. They're all plenty fast, but they all have architectural differences. What I really want to stress here is that an entire computer system is based on caching. So you have your CPU cache, then you have what is called RAM, which is essentially a system cache, and then you have your actual drive storage, which traditionally has been a mechanical hard drive. Increasingly more, it's going to be SSDs, but largely speaking, the primary problem when we start talking about information and where it's stored is how far away from the CPU it is. And that's going to be your primary differences. So anything that's on L1 is closest to the CPU. These are the things that are going to be called over and over and over again. This will probably never leave the cache. Will never get evicted. L2, very similar to L1, just not as important depending on what the algorithm's telling it. So that's going to be stored in L2, L3. Again, still very close. It's on the silicon itself for the CPU. It's still very fast. It's just not as fast as L1. Okay. And then we have RAM. RAM is very fast as well. It's just farther away from the CPU. So it takes longer, physically takes longer. The electricity it takes, the time it takes for the electricity to travel from the CPU to the RAM and back from RAM to CPU is extraordinarily long in CPU land. Because again, we're talking billions of cycles per second. So you cannot be wasting cycles requesting something from RAM if it's truly that performance intensive. So having cache on the CPU itself is incredibly important. All right. Already ranted about this. The only thing I didn't go over here on this page was branch prediction. So what this is doing for the CPU is going, okay, here are a series of instructions that we typically see, and what happens after it tends to be the same. So if that is the case, we can pre-cache, we can pre-fetch this information or even pre-process some of this information before it's actually needed. And it makes your CPU significantly faster. Miss rate on this is about 20%, which means the positive hit is about 80%, which is very, very good. However, it has turned into vulnerabilities like Spectre and Meltdown. So yeah, when that fully shakes out, we'll know a little bit more what branch prediction does. But branch prediction is still incredibly important, and it is one of the primary things that has made CPUs faster. It's also one of the primary things why the North Bridge is on the CPU now. Processing node measured in nanometers, and I have this in quotations because nanometer is not what it doesn't really mean anything anymore. At one point in time, how this was measured was the cell gate or the transistor gate. We got to the physical limitation on your transistor gates almost immediately. And now this is much closer to measuring the cell size. And now because these are measured in 3D, nanometer doesn't really mean anything. And a good example of this happened a couple years ago where Intel was struggling to get out their 7 nanometer products. And instead of just admitting defeat, they went, no, we're going to take the marketing route and say, well, this is 7 nanometer now. We're just measuring it differently, which is not great for the consumer because it doesn't mean anything anymore. It used to, not so much. So it just, everything is relative to the company. If the company doesn't change the measurements, then a shrink in process node means something. If it's not the same company, then it doesn't matter. Okay. TDP stands for thermal design power. This is another one where it's manufacturer dependent, and it doesn't mean a whole lot. You can gain a little bit off of it, but not a ton. So TDP is meant to show heat output during high but realistic use cases, high load realistic use cases. This means very, very different things for different manufacturers. So the difference between an AMD workload and an Intel workload is different, and it changes for every single architecture. So you really need to test it. And generally speaking, how you test these things is you run stress tests on them. You essentially take the entire CPU and max it out and see what heat it produces. And then you have a better idea of how much heat is actually produced, which is going to be, is you're measuring wattage, but wattage is a proxy for heat. So Yeah, the more watts that it pulls, the more heat it's going to produce, and then more intense cooling that you're going to need. And that's Intel's primary problem right now, where they just cranked up the power draw on their CPUs, which makes them more performant, but produces a lot more heat. Okay, I think we're good here. So here are your CPU manufacturers. You have your typical x86, which is going to be Intel and AMD. You have lots and lots and lots of ARM CPU companies. So Apple, Samsung, Broadcom, and NVIDIA are all examples. There are a ton more out there, particularly if you're including Chinese market. ARM in general, if I'm going to make a prediction of the future here, I think ARM CPUs are going to take over x86. That's going to take a little while though. And just like everything else, consumer oriented products, it's going to take a long time for that to saturate the market because most people don't care. Again, back to the microwave example. If the microwave works, no one cares. Right? So right now CPUs work. x86 is fine. If you're an enthusiast like I am, a ARM-based server sounds awesome. So just waiting for that to happen. And to be clear, Apple's already got their M products out there for their MacBooks. Typically, the consumer market follows suit when it's successful, and it has been successful. Okay, CPU instruction sets. x86, made by Intel, was used for 32-bit operating system. Okay, x86 includes 64-bit and 32-bit instruction sets. Okay, this is what everyone is using at this point. x64, made by Intel, was used for the 64-bit operating systems. So x64, if you don't need 32-bit at all, x64 is the way to go. Unfortunately, there's still quite a bit of software out there that doesn't require a whole lot of operating system resources. So there's still 32-bit, particularly if it's a legacy where 32-bit was the norm. Most operating systems are x86 by a long shot. And a little bit of a CPU instruction set history here. x86 was made x32 was made very, very quickly. And we just kind of patched over all the problems with x32, with x64 and x86. So the instruction set works for the CPU. Is just, it was never designed very well. ARM is much, much, much better. Again, it takes a lot of influence to penetrate the consumer market because it's very expensive to swap out all your equipment. All right, CPU architectures. Generally speaking, on this little topic here, is exposure. Again, you don't have to understand it, and you're definitely not going to understand it unless you're going to go into computer architecture, or not computer architecture, but computer engineering. But you generally want to keep your eye on these things because the architectures can make a big difference. So computer architectures are how the CPU is physically organized. So your typical CPU is going to have some sort of IO fabric. It's going to have your physical CPU core. It's going to have your caching. Yeah, that's pretty much it. Your IO fabric, caching, and cores. As system on chip, SoCs, become more and more popular, particularly with your cell phones, because that's how you would do that. You'd also include things like GPU, PCIe, and well, I guess that would still fall under IO fabric, but you get the point where everything is on a single chip. So yeah, even the CPU itself is made up of logical chunks. It's not just a thing. It's what we see as consumers as a modular package that we just call it a CPU. Very much how we call a car, but it's made of a bunch of parts. Okay, so last gen Intel, because 12th gen came out not too long ago, so we can compare and contrast here. Okay, so we got your graphics, got your memory controller. Oh yeah, this one I was forgetting, memory controller, definitely important. IO fabric, you got your communication ring through your core, so Intel separated your IO fabric out pretty much. DDR IO, so your IO fabric for your RAM. Okay. Current Intel architecture. So they actually made a huge change on their CPU front because they went to a concept of performance and efficiency cores. So when you don't need the performance, you can run off of a slower but more power efficient core. Very good for laptops. People care less about desktops, but very good for laptops. Got your memory, PCIe. Notice that this is a little bit more cohesive, so you don't have to waste so much electrical time trying to go through the silicon. Okay. Current AMD. So AMD has a completely different architecture, and they do everything through what is called a Infinity Fabric. Injects a little bit of latency, but they fix that with a lot more cache. So overall, still probably the best option at the moment. Apple, completely different because they're using ARM at this point. So this is their M2, and they're also using a system on a chip. So they have a lot more here. They have a lot more performance. And again, it's ARM. ARM architecture is completely different from x86. A little simplified diagram of what you just seen. Okay, so as we start going into particular workloads, and back to my original point towards the beginning of the presentation, what we ask the CPU to do is basically everything. If you know exactly what you want your computer to do, and that's exactly what professional markets try to do. They try to set up a scenario for a computer to do one thing and one thing really well. So an example of that is I have a little data server, a file server essentially, and it needs to do one thing, serve files. So I can hyper optimize for that scenario. Same thing can happen with your CPUs. If you know what you're going to do. So if you know, and the example I got here is CPU rendering. If you know that you're going to be using Blender, Adobe Premiere, Photoshop, anything along those lines where it requires CPU rendering, then you know what you should be optimizing for. And you don't have to worry about those other workloads because you're not going to see them. Or if you are going to see them, it's going to be relatively rare. So this is a scenario where more threads is typically better, even if it's a slower clock, because of the benefits of rendering. Because each block, if we're talking about Blender in particular, which is very good at this, it separates out each frame into a bunch of logical chunks. So each logical chunk can be processed by a core or a thread, and each thread works on that logical chunk, and then whenever it's done and it can move on. It's a very efficient way of handling resources on the computer. More threads is better in that scenario. Okay. Other software, something like Adobe Premiere, is a little bit complicated, but in general, more threads is better. There's a threshold where the software itself won't use the threads. File server, just talked about this. Okay. Generally speaking, the CPU is not a huge factor here unless you're compressing. And then once you're compressing, then it becomes more about single-threaded performance, not multi-thread. Now, if you're running a file server that has a bunch of clients on it, having more threads is helpful. All right, but you're going to be limited on your drive speed, IOs, how quickly the drive can respond more than the CPU itself. But you definitely don't want to bottleneck yourself with the CPU with a file server. Okay, web browsing, single thread intensive because of how JavaScript works. This is slowly changing, but for right now, the status quo is JavaScript is a single thread language, which is still true. Most of your sites are going to be very single thread dependent. So if you are buying a laptop for your family member that doesn't know any better, having a CPU that has a high IPC and high clock, but doesn't have as many cores is probably the way to go because it's cheaper and they're not going to notice any performance difference because there is not going to be one because it's one thread it's only using. All right. So something to keep in mind for your family members. Okay. Image and video encoding. So again, single threaded intensive for now, slowly changing. Especially when we're talking about things like streaming and OBS. There are streamers out there that have Threadripper systems that are using CPU encoding. So yeah, and then for most people, most normal people are going to use a GPU because you get so many threads there. But generally speaking, still for now, it's still single thread intensive for image and video encoding. Streaming, just talked about it. If you're doing a streaming system that does the actual encoding and playing the game, you're going to need a balance between cores and speed. All right, so this is Jim Keller, computer architect for basically all the major players in the space. Definitely worked for AMD, definitely worked for Intel. I'm pretty sure Apple as well. I'm pretty sure IBM too. Could be wrong on that, but doesn't really matter. Jim Keller is one of the best out there in terms of computer architects. So take a look at this video. Go ahead and give this a watch. It's about 20 minutes long for him explaining to you computer architecture and a little bit more thorough as well, particularly from a abstractions standpoint. So if you want to spend a little time on that, go ahead and do so. But with that said, that's all I got for this little presentation here. The next few of these is going to be computer-oriented parts. So very similar to this, we're going to be going over things like RAM, CPU, drives, and everything else that's in the computer that is appropriate for this course. So with that said, that's all I got, and I'll see you in the next one.